In this module, we'll start covering the very important topic of acids and bases, and we'll start off with a very old definition of acids and bases based on work by an individual named Svante Arrhenius. You can see the dates here, so this is fairly old work, and it involves substances dissolved in water. Arrhenius would define an acid as a substance that, when dissolved in water, produces aqueous hydrogen ions, H plus aqueous. He would define a base as a substance that, when dissolved in water, produces aqueous hydroxide ions. Let's take a look at some examples of acids under the umbrella of the Arrhenius definition. Our first example involves bubbling HCl gas into water, and when you do that, the HCl gas dissolves, and you would write it as HCl aqueous, and in the lab, you would call that hydrochloric acid. But what happens there is that HCl, that's in solution, ionizes completely into H plus ions, hydrogen ions, and chloride ions. We will say that HCl, because of this characteristic of completely ionizing, is not just an acid in water, it's a strong acid in water. And soon we'll get to defining more exactly what we mean by a strong acid. In any event, we're going to just say HCl is a strong acid. If we wrote an equation showing this, we'd say HCl dissolved in water completely ionizes into H plus and Cl minus ions. We label HCl aqueous as an acid, and not just an acid, but a strong acid. And we say that when HCl dissolves in water, it acts as an Arrhenius acid because H plus ions are generated. Let's look at another example. When the acid acetic acid is dissolved in water, it does ionize to form some H plus and acetate ions, but it only partially ionizes. For that reason, we're going to call acetic acid a weak acid in water. But right now, the important thing to see is that the acetic acid does form some H plus ions and acetate ions in water, and the fact that it does form some H plus ions in water puts it in the category of an Arrhenius acid. Let's look at an example of some bases under the Arrhenius definition. Remember, a base is something that, when dissolved in water, instead of producing hydrogen ions, it produces hydroxide ions. So an example would be sodium hydroxide that actually exists as a solid at room temperature. You have to dissolve it in water. When it does, it dissociates completely because actually it's an ionic salt, and it dissociates completely into sodium ions and hydroxide ions. Turns out that sodium hydroxide will be considered a strong base in water. If we write an equation for that, we say sodium hydroxide, when dissolved in water, is aqueous sodium hydroxide, but it dissociates completely into sodium ions and hydroxide ions. We label the sodium hydroxide as the strong base that's producing these hydroxide ions, and we say NaOH, sodium hydroxide, when dissolved in water, acts as an Arrhenius base because hydroxide ions are produced right there. How about a different base? Well, ammonia gas, when you dissolve that in water, forms aqueous ammonia. It then partially reacts with the water molecules themselves to form ammonium ions and hydroxide ions. We will constantly call ammonia a weak base because it just partially reacts. But again, the most important thing now is to see that it's acting as a base under the Arrhenius definition because it's forming hydroxide ions when dissolved in water. I want to make one note that I forgot to emphasize before. When we write the formula of acetic acid, you'll probably see me write it most often in this form, but you will also occasionally see it written as HC2H3O2, and the acetate ion as C2H3O2 instead of in this form. Not incredibly important at this point, but just keep that in mind. You might see it written either way. Let's pause for a second and ask ourselves, what exactly is a dissolved hydrogen ion, H plus aqueous? Well, it's kind of a strange beast because if you think about it, a hydrogen ion is actually just a proton. Remember, a hydrogen atom has one proton in its nucleus and one electron in a 1s orbital around the nucleus. If you remove that electron, all that's left is a proton with a positive 1 charge. Well, a proton, not too surprisingly, might be a little too unstable to exist by itself in water. Therefore, the aqueous hydrogen ion, written as H+, is often written in actually a more accurate form, which is called a hydronium ion, H3O+, where an H+ ion is bonded to a water molecule. We can illustrate that in an equation right here, the hydrogen ion interacting with a water molecule to form a hydronium ion, H3O+. If we wrote out Lewis structures of these things, and these are space-filling models here, you can see that a hydrogen ion actually forms a covalent bond with water by using one of the lone pairs on the oxygen of water as a shared pair, and the hydronium ion actually looks like this and has a positive 1 charge. The space-filling model would look like this. So here we have the hydrogen ion, which is considered to be the acid under the Arrhenius definition. In reality, what we're forming is a hydronium ion, and actually the structure here is more complicated than we're letting on. In other words, there's probably a cluster of water molecules and hydrogen ions. In any event, the acidic ion will be the hydrogen ion or the hydronium ion, but they mean really the same thing. So that means that when we showed the ionization of the strong acid HCl, or the partial ionization of the weak acid, acetic acid, those could be written in either of two ways. How we wrote them on the previous slide was HCl going to H plus aqueous plus Cl minus, acetic acid going at least partially to H plus ions and acetate ions. We could also write the same reaction like this. HCl, which produces a hydrogen ion, that hydrogen ion interacts with water to produce a hydronium ion, and what's left is a chloride ion. These two equations mean the same thing, and the only difference is whether or not we're going to write the hydrogen ion as an H plus or as a hydronium ion. If we write it as a hydronium ion, we need to show that we're working with a water molecule to balance the equation. Again, for acetic acid, we could write it as we originally did, or we could write it using a hydronium ion. Now, which way you choose to write these equations usually depends on which is most convenient to show the chemistry occurring in any particular system that you're looking at. Well, let's proceed to what turns out to be a more comprehensive definition of acids and bases, and one that we'll use for the most part exclusively in this course, although there'll be one more definition that we'll mention in a minute. This more comprehensive definition is called the Bronsted-Lowry definition. Now, this is also a very old definition from way back in around 1923, but it turned out to be a much more useful way to define and describe acids and bases, and thus is still extensively used today. I have a little footnote we'll talk about in a second. Under this definition, an acid is a substance that is an H plus donor in reactions with other substances. Now you say that sounds a lot like the Arrhenius definition. It produces H plus. The real difference here is that water is not needed. So an acid is simply an H plus donor, and this donation of an H plus does not have to occur in water, as it did in the Arrhenius definition. Now, this definition of a base actually doesn't involve the hydroxide ion, although the hydroxide ion will still be a base under this definition. Under the Bronsted-Lowry definition, a base is simply a substance that's an H plus acceptor in reactions with other substances. Again, water not necessary, although it would be involved in most reactions we talk about. So an acid is an H plus donor, a base is an H plus acceptor under the Bronsted-Lowry definition. So an acid-base reaction is then simply defined as an H plus transfer, sometimes called a proton transfer, because remember an H plus is literally a proton. And we say an acid-base reaction is just an H plus transfer or a proton transfer reaction from the acid to the base. What's kind of strange here is that we stated on a previous slide that H plus really doesn't exist, say, in water by itself, but we're still going to call them H plus transfer reactions. But again, remember the Bronsted-Lowry definition allows us to look at systems that are not in water. And in that case, these really are H plus transfer reactions. So I note here that the Bronsted-Lowry definition includes all the substances that would have been described as Arrhenius acids and bases, but expands the definition to include more substances not covered by the Arrhenius definition. And I'll try to point this out as we go along here. So let's look at an example, and we'll look at acetic acid in water, which we looked at before under the Arrhenius definition. So we have acetic acid interacting with water, forming a hydronium ion and an acetate ion. And here, looking left to right, the acetic acid is the acid because it's the H plus donor. It's donating this H here as an H plus to water, which means water here is acting as a base, which sounds strange because it's acting as an H plus acceptor. And it's producing a hydronium ion and an acetate ion. So moving from left to right, acetic acid acts as an acid because it donates an H plus to water, and in addition, water acts as a base because it accepts an H plus from acetic acid. We're looking at this under the Bronsted-Lowry definition. Now recall, acetic acid is still an acid, was an acid under the Arrhenius definition because it produced hydrogen ions or hydronium ions in water. Let's look at ammonia in water under the Bronsted-Lowry definition. Remember, ammonia acted as a base, so we have ammonia interacting with water to form an ammonium ion and hydroxide. We said ammonia was a base before because it produced hydroxide ions in water. Under the Bronsted-Lowry definition, we say ammonia is a base because it's acting as an H plus acceptor from, believe it or not, water, which is here acting as an H plus donor, and that's why water forms hydroxide, and the ammonia, which accepted an H plus, forms the ammonium ion. So moving left to right, ammonia acts as a base because it accepts an H plus from water. In addition, the water acts as an acid in this particular reaction because it donates an H plus to the ammonia molecule. So two things you want to note about these two examples. The first is that, strangely enough, water appears to be able to act as both an acid and a base depending on the situations it finds itself in. Now, a substance that can act as either an acid or a base, depending on the circumstance, is referred to as an amphiprotic substance. And we'll get into more about the special skills of water molecules in Lecture 2. And both of the examples here just to repeat ourselves, are acid-base reactions according to the Bronsted-Lowry definition. Remember, they're H+ transfer reactions. For acetic acid in water, it's an H+ transfer from acetic acid molecule to a water molecule. In the ammonia and water example, it's an H+ transfer from the water molecule to the ammonia molecule. And we're going to examine reactions like that more closely in the next few slides. One note about this footnote up here before we leave this slide: the Bronsted-Lowry definition was the second definition of acids and bases that we introduced, and in reality there have been a number of additional definitions over the years for acids and bases over the past 100 years. Later, we will introduce one of these additional definitions called the Lewis definitions of acids and bases, which turns out to be even more comprehensive than the Bronsted-Lowry. Now, regardless, the Bronsted-Lowry definition, as outlined here, will be the most useful for you to understand acid-base chemistry in this course. Now, remember, I was labeling acids and bases as strong or weak. I want to elaborate a little bit more on what these labels mean. Strong acids are very powerful H+ donors, and in the presence of only water, a strong acid completely transfers its H+ ions to water molecules to form hydronium ions at essentially 100% efficiency. Our example of a strong acid, remember, was HCl. So we take HCl, we put it in water, it reacts with water molecules, donates an H+ to a water molecule, and forms hydronium ions and chloride ions. And you'll notice here there's no equilibrium symbol. This reaction, left to right, goes 100% to completion, or so close to 100% that we call it 100%. So after the reaction, it turns out there's really no significant quantity of HCl in this form left. So if you see a bottle in the lab labeled HCl aqueous, it turns out there really is no HCl aqueous in that form. What's in that bottle is completely hydronium ions and chloride ions. Now it turns out that nitric acid is another example of a strong acid. And if we wrote an equation for nitric acid dissolving in water, we write it without an equilibrium sign because it goes completely to products, 100% to products, to hydronium ions and nitrate ions. After reaction, there is no significant quantity of nitric acid remaining in the form of HNO3. It completely ionizes. So these are examples of strong acids because they're powerful H+ donors. And in the presence of just water, it doesn't mean they can't react as strong H+ donors with other substances, but this is just a good way to define a strong acid. In the reaction with water, it drives that reaction 100% to completion. In other words, H+ ions, all the H+ ions from HCl end up on water molecules. Now, strangely enough, the strongest acid that can exist in water is the hydronium ion. There are inherently more powerful H+ donors than hydronium ions, such as HCl and HNO3. Hydrochloric acid and nitric acid are both stronger acids than the pure hydronium ion. But once they dissolve in water, these strong acids lose their H+ ions to water and are just leveled to the hydronium ion. So in water, the strongest acid that can exist is a hydronium ion. If you add an acid to water that's a stronger acid than the hydronium ion, it'll get leveled right down to a hydronium ion. Now, as you might guess, a weak acid would be a weak H+ donor. If we define it in the similar way here, we'd say in the presence of only water, a weak acid transfers only a fraction of its H+ ions to water molecules to form hydronium ions. So our example of the weak acid, acetic acid, would be written, of course, with an equilibrium sign, and what we're saying here is that acetic acid can donate some H plus ions to water, but it turns out that this reaction left to right does not go to completion. In fact, when it reaches equilibrium, most of the acetic acid is in this unionized form. Very little of it ionizes to form hydronium ions and acetate ions. So we look at it as a weak H plus donor, and that's why it's a weak acid. Nitrous acid, now remember I'm saying nitrous, not nitric, is a weak acid. If I wrote an ionization for that in water, for nitrous acid, we use an equilibrium sign because the reaction does not go to completion. And we say that when this reaches equilibrium, only a small fraction of the nitrous acid molecules transfer H plus ions to water. So when equilibrium is reached, most of the nitrous acid is in the unionized form here. So this is a weak acid. You might want to note here that it should seem strange, or I would be surprised if you didn't think this was strange, that even though there's very little apparent difference in the formula of nitrous and nitric acid is a weak acid, nitric acid is a strong acid, and I just want to bring up the fact that this shows that even small structural changes in a molecule can affect how acidic it is, and we'll talk a lot more about this in later lectures. Let's keep going with some labels here. Strong bases are powerful H plus acceptors. In the presence of only water, a strong base will completely react and form OH minus ions at 100% efficiency. Let's write an equation with our strong base NaOH to show what we mean. Sodium hydroxide goes completely to the sodium ions and hydroxide ions. That doesn't seem to be all that informative at the moment, but let's restate it like this. There's no equilibrium symbol here. Actually, sodium hydroxide is an ionic compound, and by virtue of the fact that it completely dissolves in water to the limit of its solubility, it produces the strong base OH minus. But the important point to remember here is that virtually no sodium hydroxide in solution remains in the form of NaOH. Well, what we've kind of done here is just showed that sodium hydroxide is a strong base in the Arrhenius sense because it produces hydroxide ions. Let's look at a different strong base. With this example, it's more clearly seen how it's a strong base under the Bronsted-Lowry definition. If you take oxide ion from a substance, say, like sodium oxide, dissolve it in water, the oxide ion is a strong base because it will, to the best of its ability, pick up H plus ions from water molecules to form hydroxide. It's a very powerful H plus acceptor. So every water molecule it finds, it will strip an H plus from that water molecule and form an OH minus. And by virtue of an H plus coming from the water to the oxide, it also forms an OH minus. So we get two OH minuses out of this equation. Notice there's no equilibrium symbol used here. After reaction, there's virtually no oxide ion that's remained because it was such a powerful H plus acceptor. It just went crazy and picked up H plus ions from the water molecule at 100% efficiency. Now, we want to note here, as we did with acids, that the strongest base that can exist in water is actually the hydroxide ion. There are inherently more powerful H plus acceptors than hydroxide, such as the oxide ion. But once they interact with water, these more powerful H plus acceptors, they abstract hydrogen ions from the water to form hydroxides, and thus these powerful H plus acceptors are leveled to hydroxide ions, which are the strongest base that can exist in water. Now finally, you wouldn't be surprised that weak bases are weak H plus acceptors. in the presence of only water, only a fraction of the weak base molecules will abstract hydrogen ions from the water. An example here is our ammonia, we said, which was a weak base. We have ammonia interacting with water to form ammonium ions and hydroxide ions. Notice there is an equilibrium symbol here. So ammonia is a weak H+ acceptor from water, and when equilibrium is reached, only a small fraction of the ammonia molecules have been able to strip H+ ions from water, so most of the ammonia is in the form of unreacted aqueous ammonia. Another example of a weak base is bicarbonate ion. If bicarbonate ion interacts with water, it can abstract H+ ions from water, but only slightly because it's just not a very good H+ acceptor. It is an H+ acceptor, so it's a base, but it's a weak base. So we have an equilibrium sign here, and we say, look, bicarbonate, since it's only a weak H+ acceptor in water, when equilibrium is reached, only a small fraction of these bicarbonate ions have formed H2CO3 and hydroxide. Most of the bicarbonate stays in this HCO3- form. Now we will soon deal with strong and weak acids and bases in a more exact or quantitative way, meaning we're going to do calculations. For now, we will stick with these more descriptive and qualitative terms, which will come in handy in many instances. Before we leave part 1 of this lecture, we need to look at some examples of acid-base reactions. Remember, acid-base reactions under the Bronsted-Lowry definition are simply examples of H+ transfer reactions. So let's look at the reaction of a strong acid, aqueous HCl, with a strong base, NaOH. If both of these are in water, what we get is 100% reaction, no equilibrium sign, to form sodium chloride, a salt, plus water. If we tried to write this equation as an ionic equation, what we would do is we would say, we know that HCl completely ionizes in water, so a more real way to write it would be H+ and chloride ions separated from each other. Sodium hydroxide completely dissociates in water to sodium ions and hydroxide ions. On the product side, sodium chloride in water is more accurately written as Na+ and Cl- ions, and we leave the water molecule as is. It's a molecular substance. It's not going to ionize like sodium chloride dissociates or HCl ionizes, so we leave that alone. What this gives us is an equation where there's the same thing on either side. So in other words, there's chloride on either side, so we're going to cross that out. It hasn't changed at all. It's a spectator. Sodium ions are spectators. If we take what's left, we get the net ionic equation, which gives us the essence of this strong acid, strong base reaction. An H+ ion supplied by HCl reacts with an OH- supplied by sodium hydroxide to form water. So we have our strong acid, strong H+ donor, reacting with our strong base, our strong H+ acceptor to form water. Reaction goes essentially to 100% completion. Now, if you remember that H+ ions are often written in the form H3O+, we could write this same equation in this form. We'd say the strong acid hydronium ion, which forms from the interaction of HCl with water, interacts with a hydroxide ion to form 2 water molecules, because you get H+ transfer from the hydronium ion to the hydroxide. What would be left behind is a water molecule. What would form here is a water molecule, so you form 2 water molecules. This goes essentially to 100% completion. you'd probably see this reaction written like this to save space. How about reaction of a weak acid with a weak base? Well, our example of a weak acid was acetic acid. Our example before of a weak base was ammonia dissolved in water. And remember, these are the dominant forms of these in water because acetic acid mostly stays in that form because it's a weak acid. Ammonia mostly stays in that form because it's a weak base. When they react, they're not going to react very much, thus the equilibrium sign. But if they do react, they're going to form ammonium acetate because the acetic acid is the H plus donor, and it's going to donate an H plus to the ammonia. Down here you can see this more clearly if we write this out as an ionic and actually net ionic equation. If we do that, we leave acetic acid and ammonia as is, because remember, in reality, acetic acid stays mostly in that form in a bottle of acetic acid, and ammonia stays mostly in this form in a bottle of aqueous ammonia. So we don't split those up into their ions, but we admit that when H plus transfer does take place, you'd form an ammonium ion from the ammonia and an acetate ion from the acetic acid. So looking left to right, the net result is that an H plus ion is transferred to the ammonia. The reaction does not go to completion, thus the equilibrium sign, because both the acid and the base are considered weak. Now, it is possible to estimate which side of this equilibrium is favored without doing any heavy-duty calculations. We'll demonstrate how to do that in upcoming slides. Let's look at our two other combinations of acid-base reactions. How about if we reacted a strong base with a weak acid? Well, if we take our prototypical strong base sodium hydroxide, react with our prototypical weak acid, acetic acid, we get water from an H plus transfer from the acid to the hydroxide and sodium acetate. Notice no equilibrium symbol. That's interesting. Let's write out an ionic equation. Sodium hydroxide written in the form of its ions. Acetic acid not written in the form of ions because remember it's a weak acid and stays mostly in this form unless there's an attack from a base, which is what's going to happen. On the other side we have water, which we just write as the molecular substance water, but sodium acetate is an ionic substance dissolved in water, which would mean it forms sodium ions and acetate ions. The sodium ions are spectators here, but that's all we can cross out. So the net ionic equation is that hydroxide attacks acetic acid, abstracting a proton or an H plus from the acetic acid to form water and acetate ions. Notice I use kind of a funny word here, attack, like this is some kind of war. Chemists use this lingo, and it is very descriptive. So we'd say the hydroxide attacks the acetic acid. So we have the strong base interacting with the weak acid, and this forms water and acetate ion. And I want you to note that even though these are not both strong, the strong base drives this reaction to completion. So whether or not acetic acid really wants to give up, every acetic acid wants to give up an H plus or not, because remember it's weak, the hydroxide ion or the sodium hydroxide drives this to completion and forces all of the acetic acid molecules to give up their H plus ions. So this reaction, strong base plus a weak acid, does go to completion. Our final combination would be a strong acid reacting with a weak base, and you might guess this is also going to be driven to completion by the strong acid, but let's look at it in more detail. we'll use our prototypical strong acid, HCl, our prototypical weak base, ammonia, and the reaction would give us ammonium chloride at 100% efficiency because the strong acid is going to drive this reaction to completion. If we wrote out an ionic equation, we'd say we need to write HCl as H plus and Cl minus. The ammonia, remember, stays mostly in this form because it's a weak base until it's reacted, of course. But on the left, we're just writing things before they react on the left of the arrow. So we leave ammonia alone, put it here. We formed an ionic salt here, which breaks up into its ions in aqueous solution. And we can rule out, or I shouldn't say rule out, cross out the chlorides as spectators. And the net result is that an H plus ion, which is from the HCl, an H plus ion is acting as the strong acid, interacts with the weak base ammonia to completely form ammonium ions. And the strong H plus is driving this reaction to completion. So normally ammonia is not such a great H plus acceptor, but since it's being driven to accept H pluses by these strong acids, all of the ammonia molecules react to form ammonium ion. So the net result is 100% completion, or the reaction goes 100% to the right. Now, if we remember that H plus is often written as H3O plus, we could write the same reaction as a hydronium ion, donating completely to all the ammonia molecules, H plus ions, to form the ammonium ion, and the other result would be water. When H3O plus gives away its H plus, it forms water. In part 2 of this lecture, we'll pick up the very important topic of what's called conjugate acid-base pairs.